In this lesson, we will discuss the Chinese remainder theorem for solving systems of linear congruences. So the first example of the Chinese remainder theorem appeared in the writings of a Chinese mathematician, Sun Tzu, which means Master Sun, sometime around the year 250 AD. Sun Tzu was studying astronomy and calendars and multiple Diophantine equations, and he asked the question, what number yields remainders of 2, 3, and 2 when divided by 3, 5, and 7, respectively. We can interpret this as a system of linear congruences. In terms of congruences, this question is, find x such that x is congruent to 2 mod 3, the same x is congruent to 3 mod 5, and at the same time x is congruent to 2 mod 7. The technique that will help us solve this is called the Chinese remainder theorem. So the Chinese remainder theorem says, suppose you have several moduli. So suppose M1, M2, up to MS are pairwise relatively prime positive integers, okay, so I have S pairwise relatively prime positive integers that are going to be the moduli for our system. And we have integers, we have S integers, A1, A2, up to AS. These are integers such that every AI is relatively prime to MI. So the greatest common divisor of AI and MI is 1 for each I. And let's let capital M equal the product of all the M's. So this will equal M1 times M2 up to MS. Okay. Then the system of congruences given by A1x is congruent to C1 mod M1, A2x is congruent to C2 mod M2, all the way down to AS times x is congruent to some integer CS mod MS, then this system has a unique solution mod capital M. So we know that in order for each individual congruence to have a unique solution, we require each AI to be relatively prime to MI. So we're assuming that that's the case. So each one of the individual congruences has a unique solution. So we can combine them and we'll end up getting a unique solution mod capital M, the product of all the moduli. Now let's give the proof of the Chinese remainder theorem. So, as I just mentioned, we have already shown that each particular congruence is solvable. So again, this is true because all the A's are relatively prime to the M's. So we're going to construct a solution to the system using the solutions to the individual congruences. So we'll construct a solution to the system of congruences using the solutions of the individual congruences. So first, let's list some solutions to the individual congruences. So first, let x1, x2 up to xs be integers that satisfy each individual congruence. Such that AI times xi will be congruent to ci mod mi for each I. So these x's are the solutions that we know exist to each particular congruence. So now I'm going to define another integer. So let capital M sub I be equal to capital M divided by the little mi. Okay, so capital M is the product of all the m's, so capital M sub I will be the product of all the m's except for M sub I. Well, remember all the m's are relatively prime. So since no two of the mi have a common factor, we see that the greatest common divisor of capital M sub I and little m sub I has to be 1, because capital M sub I is the product of all the m's except for mi, so it must be relatively prime to little mi. So if capital Mi is relatively prime to little m sub I, then we can find the inverse of capital M sub I mod little m sub I. Then we can find capital M sub I inverse, okay, so the multiplicative inverse of capital Mi mod little mi. So we have that capital Mi times capital Mi inverse will be congruent to 1 mod little mi, and this is true for each I. Now we're ready to construct the solution to the system. Then we will show that x0 defined by x0 is defined as x1 times capital M1 times capital M1 inverse plus x2 times capital M2 times capital M2 inverse mod m little m2 plus, and we're going to do this for each x, so it's going to end at xs times capital ms times capital ms inverse. Okay, so we're going to show that this x sub 0 is a solution of the original system of congruences. So now let's see that x sub 0 is a solution to the system. So I rewrote x sub 0 here. First note that little mi divides all the capital mi's except for when the subscript is the same. So mi divides each capital MJ except for capital MI, because capital MI is the product of all the little m's except for MI, but that factor of little mi is in all the other capital MJs. So that's the first thing to note. Then let's plug in x0 into each of the original congruences. So, for example, if I have AI times this x0, then I can distribute AI. So this is AI times x1, capital M1, capital M1 inverse, plus AI x2, capital M2, capital M2 inverse, all the way to AI times XS times MS times capital MS inverse. Then this expression will be congruent to AI times xi times capital Mi times capital Mi inverse when the modulus is little mi. This is because the previous note that all of these other terms, all the terms except for when the subscript is I, will be divisible by little mi. So they would all equal 0 mod mi. So the only term that's going to remain is a sub I times xi capital Mi times capital Mi inverse. But capital Mi times capital Mi inverse is congruent to 1 mod Mi. So this is congruent to Ai times Xi mod Mi. Okay, again, because when I multiply capital Mi times capital Mi inverse, I get 1 mod Mi. But Xi is a solution to the original congruence, so we know that Ai times Xi is congruent to Ci mod Mi. Thus, if we plug in x0 into any of the individual congruences, it satisfies the congruence. So x0 is a solution of each congruence. So, and therefore x0 is a solution to the system of congruences. We claimed that x0 was the unique solution. So let's prove the uniqueness. Let's suppose that we have another solution to the system. So to show uniqueness, mod capital M, suppose we have another solution, let's call it y0. So suppose y0 is a solution of the system as well. So suppose y0 is another solution of the system. Well, remember that all the AIs and MIs are relatively prime. Okay, so since the GCD of AI and Mi equals 1, each of the individual congruences has a unique solution. Each congruence has a unique solution mod little mi. So x0 and y0 must be congruent mod little mi. So y0 must be congruent to x0, which must be congruent to xi mod mi, because each individual congruence has a unique solution. So since x0 and y0 and xi are all solutions, they must all be congruent, mod mi. Okay, so this is for each I. So if y0 and x0 are congruent, mod mi, then by definition of congruent, little mi divides the difference x0 minus y0 for each little mi. So we see that mi divides x0 minus y0, but all the mi's are relatively prime. So the product of all the mi's will also have to divide x0 minus y0. Okay, so since the mi are pairwise relatively prime. We know that the product of all the m's, m1 times m2 times all the way up to ms, this must also divide the difference x0 minus y0. So we know this is true because each of the m's divides x0 minus y0, and none of the m's have a factor in common. But this is the same as saying that capital M divides x0 minus y0. So then capital M divides x0 minus y0, and by definition, x0 is congruent to y0 mod capital M. So we see that any solution to this system is congruent to x0 mod capital M. So that finishes the proof of the Chinese remainder theorem. So we can use the Chinese remainder theorem to solve systems of linear congruences. Now let's go back and solve the question that Sun Tzu asked almost 2,000 years ago. Let's solve Sun Tzu's system of congruences. Okay, recall this was, the congruence was x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. So let's compare this system to the statement of the Chinese remainder theorem. So if we look at this system, we see that for Sun Tzu's system, all of the a's will be equal to 1. And then the solutions to the individual congruences will be 2, 3, and 2. So x will be congruent to 2 mod 3, x will be congruent to 3 mod 5, and x will be congruent to 2 mod 7. And the moduli are going to be 3, 5, and 7. So in the Chinese remainder theorem, we'll see that AI is going to equal 1 for A1, A2, and A3. The solution to the first congruence, x1, will be 2. The solution to the second congruence will be 3. And the solution to the third congruence is 2. So our moduli, M1 is 3, M2 is 5, and the third modulus is 7. So when I multiply these moduli together, I get capital M is going to equal 3 times 5 times 7, which is 105. Okay, so then M1 would be the product of 5 and 7. So M1, capital M1 is 35. Capital M2 would be 3 times 7, or 21. And then capital M3 would be 3 times 5, or 15. Okay, so let's find the inverses of these capital M's. Okay, so let's find their inverses. Well, we need to solve the congruence 35 times m1 inverse will be congruent to 1 mod 3. So m1, capital M1 is 35, so 35 times m1 inverse would equal 1 mod 3. 35 is 2 more than a multiple of 3, so I can replace that with its residue. So this is the same as 2 times m1 inverse is congruent to 1 mod 3. Adding 3 to 1, I get 2 times m1 inverse is congruent to 4 mod 3. And I can divide by 2, which is relatively prime to the modulus, to see that m1 inverse will be congruent to 2 mod 3. Okay. Then m2 is 21, so 21 times m2 inverse will have to be congruent to 1 mod 5. Well, 21 is already 1 mod 5, so m2 inverse is 1 mod 5. Similarly, we'll see that m3, which is 15, times m3 inverse will have to be 1 mod 7, but 15 is already 1 mod 7, so when I rewrite it as 1, I see that m3 inverse will be congruent to 1 mod 7. So let's put all this together. So we see that the solution to this system, which is x0, we call that x0, so it's x0, it's going to be equal to x1 times capital M1 times capital M1 inverse, so that will equal 2 times 35 times 2 plus x2 times M2 times M2 inverse, so this will equal 3 times 21 times 1, and then plus x3, which is 2 times capital M3 times capital M3 inverse, which is 1. And we see that x0 is 140 plus 63 plus 30, which is 233. So if I plug in 233 into each of these congruences, it will satisfy all three. So all solutions must be congruent to 233 mod 105. So all solutions are congruent to 233 mod 105. And so the smallest positive solution would be 23, because 233 is congruent to 23 mod 105. So the number 23 is the smallest positive solution to this system of linear congruences. So we use the Chinese remainder theorem, and we use the construction of x0 to generate a solution. I'm going to show you an alternate solution to this same system. What I'm first going to do is find a solution to the first two congruences. X is 2 mod 3 and X is 3 mod 5. So first, I'm going to solve just the first two congruences. X is congruent to 2 mod 3 and X is congruent to 3 mod 5. So if X is congruent to 2 mod 3, then I know that X is 2 more than a multiple of 3. So this implies that X equals 3 times an integer plus 2 for some integer t, and X is 3 mod 5, so then I can plug in 3t plus 2 for X and see that 3t plus 2 must be congruent to 3 mod 5. Let's solve this congruence for t. Subtract 2, we see that 3t is congruent to 1 mod 5, and that is the same as, that is congruent to 6 mod 5. So if I divide by 3, I see that t must be congruent to 2 mod 5. So I'm going to rewrite t as an integer times 5 plus 2. So this tells me that t must equal 5 times some other integer, it's called s, plus 2. For some integer s. Okay. Now let's back substitute for t. So we saw originally that x is congruent to 3t plus 2. So I'm going to take this expression, 5s plus 2, and I'm going to substitute that back in for t in this expression. So we'll get a congruence for x mod 15 by doing this. Then x, which is 3t plus 2, must equal 3 times 5s plus 2 plus 2. And I see this equals 15s plus 8. Another way of saying this is that x is congruent to 8 mod 15. So I've just found a solution to the system of congruences x is 2 mod 3 and x is 3 mod 5. We see that x must be congruent to 8 mod 15. So I'm going to repeat this process with x congruent to 8 mod 15 and x congruent to 2 mod 7. So second, I'm going to solve x congruent to 8 mod 15 and x congruent to 2 mod 7. I'm going to use the same technique. I'm going to write x as 8 more than a multiple of 15. So we have x equals 15s plus 8. And that must be congruent to 2 mod 7. Let's solve for s. So 15s is congruent to -6 mod 7 when I subtract 8. But -6 is the same as 1 mod 7. And 15 is also 1 mod 7. So I can write the left-hand side as just s, and -6 is 1 mod 7. So I can write s as 7 times an integer n plus 1 for some integer n. Now we're going to back substitute again. So I have s is equal to 7n plus 1 for some integer. So I'm going to take 7n plus 1 and substitute that back in for s. And we see that we'll obtain a congruence for x mod 105. So then x will equal 15 times the quantity 7n plus 1 plus 8. When I expand this, I get that x is 105 times n plus 15 plus 8, which is 23. In other words, x is congruent to 23 mod 105. So we get the same solution that we got using the formula from the Chinese remainder theorem. So this is an alternate way to solve a system of linear congruences. You can solve them two at a time using this technique. It's really the substitution method and the definition of congruence.